The topic of our lesson is written here on this slide. Initial value problems for ordinary differential equations. But before we start the lesson, before we start to consider the methods for solving ordinary differential equations numerically, I want to ask you, do you remember what is an ordinary differential equation in general? Because we should consider some properties of these equations. So first we start from the second point, some theory of initial value problems for ordinary differential equations. And just after that we come back to the problem statement and we consider some real life problem that, good morning. Okay, in this case I will well, I repeat that we start from the second point. We review some elementary theory of initial valued problems. This is a general problem statement for ordinary differential equation. Y is a known function that depends on x. F is a known function that depends on x and y. So x is a variable, y is a function. But f is the right-hand side of this equation, and f depends on both x and y. Let's consider some simple cases of ordinary differential equations. Well, I can write it on the board, but I think for simplicity, I can write it using Word on the screen. I think it will be better for those students who attend this class online. Well, I share all of the screen. Now you will see the Microsoft Word. So let's consider this equation. Y prime equals to, for example, 1. Yeah. Y prime equals to 1. And let me remind you that y is unknown function. So our goal is to find this function y of x. But we know that y prime equals to 1. The question is, what is y of x? Who can answer this simple question? If y prime equals to 1, what is y of x?
X.
X. Right. But this answer is correct, but not complete. Y of x equals to x. It's not complete answer, because I can give you a lot of examples, a lot of functions y of x such that y prime equals to 1. Y of x equals to x is not a unique function that has a property that y prime equals to 1. What answer will be complete? What answer is complete? Not y of x equals to 1, but if you even don't remember the theory of differential equations, you can guess.
+1.
+1. Okay. It's another example of a function that has a derivative 1. But the answer still be not complete, because it's just a particular case of the functions with property y prime equals to 1. No ideas. But for example, x plus 2. What will be the derivative of x plus 2? Derivative of x equals to 1. Derivative of 2, 0. That's why this function also has a property that y prime equals to 1. X plus 3, the same situation. So what will be their complete answer? Y of x equals to, right, x plus any constant. X plus any constant. In the theory of differential equations, this solution is called general solution. If I have such equation, there are infinity many number of solutions. Not only one, but infinity. X plus constant, any constant. But also in the theory of differential equations, we consider such problems that called initial value problem. It means that I have not only this equation, but also I have some point x 0 that called initial point, and I know the value I know the value at this point. For example, let it be, it can be any point, but I know it. Let's consider x0 equals to 0. And I know that y of x0, for example, equals 2. I mean, this is an equation, and this is initial value for this equation. x0 equals to 0, and y of x0 equals 2. It means that I can fix this constant from this initial condition. If I have this general solution, y of x equals to x plus const, and y of 0 equals to, what is the value of this constant that will satisfy this condition? Y of 0 equals 2. One. Substitute constant equals to 1 and x equals to 0.
Oh, it's 2.
Did you get 2? Constant equals 2. This constant, from this initial condition, we can find that the constant equals 2. Well, let me repeat again from the beginning. We are going to find the function y of x that has a known derivative y prime equals to 1, and this function satisfies initial condition y of x0 equals 2. In general, if this equation is simple, we can solve it and we can find the general solution. This general solution usually, not usually, but always, it always depends on some constant, and this constant can be fixed from this initial condition. So these are main points from the theory of differential equations that will be useful for us. Well, let's consider another example. We start from the very simple example. Let's consider an example that is a little bit harder. Y prime equals to x. First question, what is the general solution to this problem? Y prime equals to x. What is y of x?
X plus a constant.
What? Sorry.
X plus a constant.
X plus constant. But compute the derivative of x plus constant. What is the derivative of x plus constant?
X.
No,
One.
It's 1.
it's 1. So y prime equals to 1. But in our case, y prime equals to x. Why should be this? Why should be such a function that has a derivative x? This question is for all the students. The students who connect to our lesson online, you can also suggest your solutions. You can write your solutions in chat because this solution is very simple, or you can tell me your solution using your microphone. If y prime equals to x, what is y? I just repeat what's written here. Y prime of x. Y depends on x equals to x. So what is y of x? What function?
X plus 1.
X plus 1?
Constant.
X. But you already told me this answer. If you take y equals to x plus constant and you compute the derivative of x plus constant equals to 1. But y prime must be equals to x. The question is, what function has a derivative x?
Constant.
A constant has a derivative 0. What function has a derivative x?
X square.
X in square. But your answer, yes, you are on the right way. But x square, if we consider x square, what will be the derivative of x square? 2x.
2x.
2x. But in our case, we have x. So
Yes.
if you consider y of x equals to x squared, the derivative of x squared equals to 2x, but we should have x. What function I should take that has a derivative not 2x, but x?
Another one. Another.
Of course another, because it's not correct answer. This answer is wrong. Because x squared prime, the derivative y prime equals to 2x, but our problem statement is that y prime equals to x. No idea. X squared, you are on the right way, but
X squared divided by 2.
right, very good. X squared divided by 2, x squared over 2. So the answer is x squared over 2. Derivative of this function is to x. Derivative of x squared equals to 2x, and to get x, we should divide it over 2. Well, but as on previous case, this answer is just a partial case. The general solution will be x squared over 2 plus some constant.
1.
Because constant may be any constant. So in general, we have a lot of solutions to this problem. And to fix one of the solutions, I should specify initial condition. Let's consider the same condition, that x0 equals to 0 and y of x0 equals 2. The same initial condition as in previous case. Well, so it means that y of x0 equals 2. And the same question, what is the constant? You have a general solution. You have initial point, y of x0, it must be 2. What is the value of constant in this general solution?
2.
It should be 2, right?
2.
As in previous case, the value of the constant equals 2. The value of the constant equals 2. Well, I can take any other initial condition. The initial condition may be different. Let's consider, just for example, let's consider another initial condition. For example, x0 equals to 1, not 0. And in this case, we will have f of 1, sorry, not f, y of 1 equals 2. What is the value of constant that satisfies this initial condition? No, not 1. The function y of x is written like this: x squared over 2 plus some constant. But we know that y of 1 equals 2. What is the value of constant? 2? No. Please, 0.
X.
Constant cannot be x. Constant cannot be x.
Yes.
What is the value of the constant that satisfies this condition? Y of 1 equals 2. What you should take? You should substitute here 1. To find a constant, you can substitute here 1 instead of x. y of 1 equals 2. What is the value of constant?
One.
No. Y in square over 2 plus constant equals 2. What is the value of the constant? What is 1 square over 2? What is the value of 1 square over 2?
4.5
0.5.
plus 1.5.
Yes. The value of the constant here equals to 1.5. 0.5 plus 1.5 equals 2. So the value of the constant equals to 1.5. Okay. We review some simple cases. And now let's consider a little bit complex case. This one. Y prime equals to y. And let's consider the same. The first initial condition. What is the value of y? Well, now y prime equals to y. What function I should take that has a property that y prime equals to y?
Y plus constant.
Sorry, I don't hear.
Y squared.
Y squared.
Y squared.
Y is a function of x. When I ask you about y, you should give me the function that depends on x. Y prime equals to y. But the unknown function y of x, it depends on x. In the right-hand side, it must be some formula that depends on x. Like in our previous cases. What solution we already consider? Y of x equals to x. Y of x equals to x squared over 2. The right-hand side depends only on x. It cannot depend on y, because y is unknown function. But we know that the function y has a property that y prime equals to y. Again, this equation, this differential equation is also very simple. And I think you know the solution to this equation. The derivative of the function equals to the function itself. If you take, for example, if you take x squared, what is the derivative of x squared? Y prime equals to 2x. Y equals to y prime. No, x squared doesn't equal to 2x. You can take any other function. For example, let's consider sinus x. What is the derivative of sinus? Cosine. Y of x and y prime of x are the same? No. Y of x equals to sinus x. Y prime equals to cosine x. But this equation tells us that y prime equals to y. And I ask you, what function will have the property f of x? But f of x is a general form of the y prime equals to f of x. But what is f of x? This is my question to you. What is f of x? Give me the formula for f of x.
X plus C.
X plus c. But x plus c is the solution to the equation y prime equals to 1 that we consider as a first example. This equation is another equation.
X to the power of unknown plus constant.
Sorry, please repeat. One over 3. 1 over 2 is a constant. Derivative of a constant equals to 0. Well, no ideas. I think that this question is not very complex question.
X to the power of 2 plus constant.
No, x power 2 plus constant we consider right now. If you consider x power 2 plus constant, x power 2 plus constant, the derivative of x power 2 plus constant equals to 2x. Y prime is not equals to y. Well, again, I told you several times that there are a lot of functions, and only one function, only one function has this very, very good property that derivative of this function equals to the same function. What is this function? Derivative of sine equals to cosine, derivative of cosine, sine, derivative of x squared equals to 2x, different functions. But what function have the same derivative? The same derivative as the function. E power x, exponential function. The exponential function.
E power x.
E power x.
Plus constant.
Of course, plus constant, yes. But their solution, it's our x, exponential function. This function has a property that derivative of e power x equals to e power x. If you compute the derivative of e power x, the derivative will be e power x. Y prime equals to y. y prime equals to y. And we have two different options. First, I can write here plus constant, and it will be true. So I can write e power x plus constant, because e power x plus constant will have the same derivative as no, I'm sorry, not plus constant, because if you consider e power x plus constant, what will be the derivative of e power x plus constant? E power x plus constant equals to e power x without constant, because the derivative of constant equals to 0. And we have that y prime equals to y. In this type of equations, when the solution is an exponential function or sinus, I can write not plus constant, but time constant. Let me see dot. Yeah. Constant times e power x. In this case, derivative of constant, any constant, times e power x will be constant times e power x. Y prime equals to y. And this constant must be fixed from the initial condition. Suppose that we have the same initial condition, y of 0 equals 2. Y of 0 equals 2. What will be the value of the constant? Substitute x in this equation and find the constant, please. What will be the value of the constant? The value of the constant is 2. You can substitute it. Constant times e power 0 equals 2. E power 0 equals 1. That's why constant equals 2. So the partial solution that satisfies this initial condition 2 times e power x. Two times e power x. Well, we consider now just some very simple examples. We consider 3 simple examples of ordinary differential equations. And in the course of differential equations, I think you're consider more examples, but for our goal, for our purposes, it's enough. Let me repeat the main points. In this type of equation, the unknown is a function, and we are going to find the function that satisfies some property. The property is that we know the derivative of this function. And in general case, in general problem statement, the right-hand side is some function that depends on x and y. So let me delete all of this. So in general, the right-hand side is some function that depends on x and y. What function? We consider this function may be constant 1, this function may be x, this function may be y, or even write as, for example, x times y plus x, something like this. Any function that depends on x and y, for example, x squared plus y power 3, something like this. Of xy can be any function that depends on xy. But we know this function. We know f of xy. And to fix the one solution from the general set of solutions, we should know the initial condition y of x0 equals to y0. x0 and y0 are known values, known values. And this point, x0, y0, fix one solution from their general solution. Well, we review some information from the theory of differential equations. And now let's consider some, or maybe one feature I can tell you that this equation is called the first order equation, but in some cases we can consider so-called second order differential equation that know the second derivative of the function y, and this second derivative equals to some function of x, y, and y prime. The second order differential equation. The order of equation means the order of the highest derivative. This is the second order differential equation. This is the first order differential equation. The differential equations are very important because there are a lot of processes, a lot of objects that can be described by means of ordinary differential equations. Let's consider some example. suppose that we have a pendulum, and suppose that we want to find an equation, not equation, but the function that described the motion of the pendulum. The picture is written here. I just repeat this picture. Well, suppose that we have a pendulum. The length is fixed. The length is fixed. And suppose that I take this pendulum and I free it. What will be the motion? The motion of the pendulum. If the initial, I fix some initial angle, and after that, I free, yes, free. How it will motion? What will be the motion of the pendulum? How it will move?
Swing.
Swing.
Yeah.
Swing, right? Something like this.
Yes.
How to describe this swing? How to describe? This is a length. The length is fixed, L. And how, in this case, how to describe the swinger of the pendulum? We can introduce the angle between the vertical line and the pendulum. And the swinging of the pendulum can be completely described by this value of angle, the value of the angle. If the angle is 0, it means that the pendulum is a vertical position here. If the pendulum moves here, let's consider this angle as a positive, plus. Here, minus. And usually this angle is denoted by the Greek letter theta. It's a Greek letter theta, and this theta corresponds to the angle of the pendulum and the vertical line. And of course, the angle will change in time. The angle will depend on time. Theta depends on time. Because the pendulum is swinging and the angle is changed. And from the course of physics and from the course of differential equation, we know that the swinging of the pendulum, the changing of this angle theta, is described by means of this differential equation, second order differential equation. There, so the second derivative of theta, d squared theta over dt square, plus g over L sinus theta equals to 0. where L is the length of the pendulum, G, so-called gravitational constant of the Earth, and theta is the angle. By the way, do you know what is a gravitational constant or not? Yes? 9.8. Right. Right. G is a gravitational constant. L is the length. Theta is the angle. T is time. And to find the solution to this problem, we need to fix some initial condition. And the initial condition is very simple. We know some initial moment of time. Let's denote it as t0. And at this initial moment of time, we know the angle theta of t0, and we know the velocity. Velocity from the mathematical point of view is a derivative. Theta prime equals to some theta 0 prime. So we know the initial angle and we know the initial velocity. So we have the problem, the initial value problem for differential equation. Well, and also from the mathematics, from the mathematical analysis, we know that if the argument is small, then sinus x approximately equals to x when x is a small. In this case, if the angle theta is small, we can say that the sinus theta approximately equals to theta. And we can simplify this differential equation and write it in this form. Second derivative of theta plus g over L theta equals to 0. I replace sinus theta with theta. And initial condition, theta 0 and theta 0 prime. But this equation, the second equation, will describe the motion of the pendulum only when the angle is small. Only when the pendulum moves near the vertical line, when the angle is small. If the angle is large, the second derivative is not described, the motion of the pendulum. We should use the first one with sinus. But the last problem can be solved by a standard differential equations techniques. And the first problem cannot be. No differential, no techniques to solve the first equation. Nobody can solve it. I mean, nobody can solve it analytically. nobody can find the exact solution, as we done for our simple examples. For example, something like y prime equals to 1, we can guess, we can find the exact solution. But for this very, very simple, very short equation, nobody can solve it. Nobody can find the exact solution. For this equation, we can find the solutions. But the last equation can describe the motion of the pendulum only for small angles. When the angle is large, we should use the first one. But the first one we cannot solve. And during this lecture, we consider the methods how to find the solutions to differential equations numerically, how to solve the differential equations that cannot be solved by standard techniques. How to solve the differential equations that don't have simple solution. Well, again, any textbook, any lecture on differential equations, there are a number of methods for explicitly finding solutions to first order initial value problems. But in practice, just a few of such problems can be solved exactly. Well, now we come back to their initial problem statement. dy over dx equals to f of x and y. X is a variable. X is changed between a and b. A and b is some given numbers, lower bound and upper bound. And we know the initial condition. Y of a equals to y0. We know the initial point, a, and we know the initial value, y of a. Maybe later, if we will have time, we extend these methods for system of first order differential equation. And also we consider the relationship of system of this type to their general high order initial value problem. Well, again, if we consider some initial value problem, dy over dx equals to f of xy, I can write this problem as y prime equals to f of xy, and initial value y of x0 equals to y0. The exact solution to this problem is some function y of x. Y of x is the exact solution. But how to solve this problem numerically? How to get approximation to the exact solution? And what will be this approximation? Again, it's hard to expect that their differential equation can be solved exactly, and we find the formula given y of x as a function of x, and as an approximated solution we consider this table, the table of function values. Xi and yi. The values of x, we can compute it very simple. We know the initial point x0. We know it from their initial condition. After that, we can take some given step, and we can compute x0 plus step, and we can take this point as x1. After that, x1 plus some step h, and we compute x2, and so on. So the values of x's can be computed very simple. The first value of y we know from their initial condition. And the question is how to compute all other values of y. y1, y2, y3, and so on. Here, yi, for example, y1, y2, is a computed approximate value of y of xi. Y of xi will be our notation for the exact solution at the point xi. And if we have such a table, the table of values, we can construct approximation to the function y of x. We can do it, for example, using Lagrange or Newton interpolating polynomial, or we can use least square interpolating technique to find the function that approximates the values given in the table. Let me repeat again that our goal now is to compute the values of y here, y1, y2, and so on. And yi is approximation to the value of y of xi, their exact value of their function, of the exact solution at the point xi. And on the second half of our lesson, we will consider the method, how we can compute these values of y. How we can compute it using so-called Taylor's series approach. Well, let's have a break now. I stop sharing for the break. During the break, I stop sharing, and let's have 15 minutes. 15 minutes break, and 10:50 we will continue. Now it's time for break. 10:50 we continue. Please, 5 minutes, and after 5 minutes we start the lesson. Okay. Let's continue our lesson. I share the screen. We stop here, this point, that we have a differential equation. We cannot solve it by standard technique. We cannot find the exact solution y of x, but we can find this table that contains x's and y's. Here y is approximated value of y of xi, and after that we can find interpolating polynomial that interpolates the function. Well, to illustrate the method, let's consider some concrete example. I told you that the right-hand side can be any function f of x and y. In particular case, y prime can be cosine x minus sinus y plus x squared. So this is the right-hand side. And the initial condition is y of minus 1 equals to 3. So the basis of the method is a Taylor series for x. We can write the Taylor series in this form. We already wrote it several times on different lessons because the Taylor's formula, Taylor series, is a basis for many methods, especially for the methods for solving differential equation. Y of x plus h, here x is some point and h is a step. Y of x plus h equals to y of x plus h times y prime of x plus h squared over 2 second derivative of y plus h power 3 over 6 third derivative, and so on. The terms that have the power of h power 4 or higher. The derivatives appearing here can be obtained from the differential equation. The first derivative. The first derivative we know exactly from the equation. The second derivative, we can differentiate their first derivative. Third derivative, we can differentiate the second derivative, and so on. We can do it if we know the right-hand side, and if the right-hand side is a relatively simple function. Suppose that we decide to use only terms up to and including h power 3 in the formula. The terms that we have not included start with the term h power 4, and they constitute collectively so-called truncation error. and the resulting numerical method is said to be of order 3. The order of the Taylor series method is n if terms up to and including h power n are used. And at each step, the local truncation error is of order h power 4, since we have not included terms involving h power 4, h power 5, and so on from the Taylor series. Thus, as h tends to 0, actually we cannot take h tends to 0, but if h is very small, the behavior of the local errors should be similar to constant times h power 4. Unfortunately, we don't know the constant, but h power 4 is very good. For example, if we have h equals to 10 power minus 2, then h power 4 equals to 10 power minus 8. So their error will be small. So the error in each step should be of the magnitude 10 power minus 8. But after several hundred steps, these small errors could accumulate and spoil the numerical solution. At each step except the first one, the estimate yk of the real value y of xk already contains the errors, and further computations continue to add to these errors. Let's consider two important definitions. The local truncation error is the error made in one step when we replace the infinite process by the finite one. In the Taylor series method, we replace the infinite Taylor series for y of x plus h by a partial sum. So we just truncate all of the terms up to and including h power 4, and we use only the terms up to h power 3. The accumulation of all of these many small local truncation errors gives us the global truncation error. And it is known that if the local truncation errors are of order h power n plus 1, then the global truncation error must be of order h power n. Because the number of steps necessary to reach an arbitrary point x having started at a point x0 is x minus x0 over h. Well, this is the general information about all of the approach that called Taylor's series approach. And the simplest case of the Taylor series method is called Euler's method. We already use this notation, Euler's method, for the method for solving non-linear equations. And here, the idea of the Euler's method is more or less the same. Well, let's take the Taylor's formula, this one, and let's truncate it at this step. So let's remove all of the terms up to and including h power 2. What will we have after this? If we remove all the terms up to and including h power 2, we will have only their two terms in the sum. Well, this is very important that I repeat it on the board. This formula, Taylor series, allows us to compute the value of the function at the point y of x plus h. H is a step. X can be any x. For example, from this table, it can be x number I. And I can compute it as y I, or I can write it as y of xi plus h times y prime of xi plus h square over 2 y second derivative of xi plus, and so on. This is a Taylor's formula. This equality is exact. So the value of the function at the point xi plus h can be computed like this exactly. But the idea of the Euler's method is to truncate all of the terms starting from this up to and including h power 2. We consider only first two terms in the Taylor series. Of course, if we remove these terms, this equality becomes not exact, but approximately equals. Well, and finally, the main feature of Euler method is that here is written y prime of xi. But what is y prime? We know y prime from the differential equation. It's the y prime is the right-hand side of a differential equation. And I can write that y I plus 1, I denote y I plus 1. I denote y of xi plus h as y I plus 1, the value of the function at the next point, equals to yi plus h times of xi yi. This is the main formula for the Taylor series for the Euler method. Please write it, fix it, and remember it. This formula is the main. This formula has the obvious advantage of not requiring any differentiation of f of x, y. The local truncation error of Euler's method is O h squared, and the global truncation error is O of h, order of h. So the Euler's method is a first order method for solving differential equations. To understand how it works, let's solve some exercise. Let's solve some example. I don't remember, is it written here or not in the end? Oh, it's written complex examples. Okay, let's start from the very simple example. I will write it here on the board, and let's solve this example. Y prime equals to y, and x0 equals to 0, y of x0 equals 2. We already solved this example, and you know the actual solution. That's why this equation is very important, because it's very simple to compare the actual solution and the numerical one. Well, let's try to solve this equation with step h equals to 0.1. Let's solve this equation using Euler's method. And let me repeat the main equation for the Euler method. Y I plus 1 equals to yi plus h times f of xi yi. If we know x0 and y0, we can compute y1. If we know y1, we can compute y2. If you know y2, you can compute y3. And on this way, step by step, we can fill this table. We can compute y1, y2, y3, and so on. Let's do it. I ask you to solve this equation. Using Euler's method. The method is written here. The initial condition is written here. You can rewrite it, and I just write this equation on the board. I just rewrite it. Y prime equals to y, and y of 0 equals 2. So it means that x0 equals to 0, right? H is 0.1. What can we say about x1? What will be the value of x1? If h is 0.1, what is the value of x1?
x0 is 0. x0 is 0. What is x1? 0.1. What is x2?
0.1.
And so on. x3 is 0.3, x4 is 0.4, and so on. Well, it's very simple. What can you say about y? What is the value of y0? What is the value of y0? y0 we know from the initial condition is 2. Well, and our goal now is to find the value of y1. y1 we can find using this formula. y1 equals to y0 plus h times f of x0 y0. y0 we know. What is f of x and y? What is f of x, y in our case? No. F of x, y is the right-hand side of this equation. In our case, this right-hand side is very simple. It doesn't depend on x. It depends only on y. F of x, y is y. Well, I write it. What is f of x and y in our case? It's y. It's the right-hand side of the equation, because the general form of the equation is y prime equals to f of x and y. In our case, the right-hand side is y. Please compute y1. What is the value of y1? Compute the value of y1. I show it like this. Right. Excellent. The value of y1 is 2.2. The value of y1 is 2.2. Y. y1 equals to y0. y0 is 2 plus h. h is 0.1 times f. But f is y. And we substitute here y0 times 2. And we have 2.2. y1 is 2.2. How to compute y2? We should use the same formula. We should just update indexes. y2 equals to y1 plus h times x1 y1. This is y1. So y2, we should take the previously computed value of y1 and computed. I asked to do it all of the students, including the students who connect to our meeting online, because on the exam you should solve it. Well, one of you gets this problem. What is the value of y2? You should take y1, 2.2, and substitute it here into this formula. Do you compute? What value? You can type your solutions in the chat. You should take the previous value 2.2 plus h is 0.1, right?
Yeah.
Plus y44 for 2.24 for 2 times 0.1 times 2.2, and when we compute the sum, it will be 2.42, I think, no? 2.42, right?
Yes, 42 is correct.
So how do you do f of x1?
What?
F of x1, y1.
Again, what is f of xy? In our case, it's the right-hand side. It's the right-hand side of the equation. In our case, is just y. A little bit later, we consider more complex example, but now f of xy is just y. And I substitute here y1. y1 is 2.2. y1 is 2.2. I substitute it here and I get the answer 2.42. How to compute y3? The same. You should take 2.42 and substitute it into this formula. And so on. Step by step, we can fill all of these cells of this table. Is it clear or not? To understand it better, let's solve another equation. Let's solve another equation. It's written here. It's written here on this exercise. Let's consider the exercise 1 under the letter okay, let it be B. Let it be. Exercise 1, letter B. What is the right-hand side of this equation? Letter B. Y plus y over x. What is x0? X0 is 1. What is y of x0? X0 is 2. What is h? 0.25. Well, let's consider exercise 1 under the letter B. Y prime equals to 1 plus y over x. X0 is 1. Y of x0 is 2. And h is 0.25. Let's use the same formula to find the values of y. What is the equation? Y equals to y prime equals to 1 plus y over x. What is the initial condition? Y of 1 equals 2. What is the step? H equals to 0.25. Let's start to fill the table. What is x0?
One.
X0 is 1. What is x1? 1.25. X2? 1.5. X2 is 1.5. What is y0? From the initial condition, y0 is 2. Bad. And the main step. What is y1? We can use this formula to compute y1. Use this formula to compute y1. What is the value of y1? How to compute it? Again, I just rewrite the formula for I equals to 0. If I equals to 0, from this general case, we have that y1 equals to y0 plus h times f of x0, y0. What is f of x0, y0? No. In general, what is f of x, y? Without concrete point. What is f of x, y? It's the right-hand side of the equation. It's the right-hand side of the equation. In our case, what's written in the right-hand side? 1 plus y over x. And you should substitute in the right-hand side x0, y0. What will be the value of the right-hand side? For x0, y0. Yes, 1 plus 2 over 1 equals to 3. So the value of f of x0, y0, that will y0, 2 plus h, 0.25 times 1 plus 2 over 1, 3. And what we will have as a final answer? Yes. Yes. Let me repeat the same computation in Word. I think it will be better for those students who connect to our meeting online. y1 equals to y0 plus a times f of x0, y0. And in our case, y0 equals 2 plus 0.25 times 1 plus 2 over 1. And it equals to 0.0 plus 2.75. Right. The value of y1 equals to 2.75. Very good. But how to find the next value, y2? We can use the same formula. Here, the index 1, right? y1 plus h f of x1, y1. And you should substitute into the right-hand side of the equation the values of x1, y1. It's computed, and after that we compare the answers. Well, how to compute y2? The formula is written here, and you should just substitute their values. What is the value of y1? 2.75. What is the value of h? 2. And the main point, what is the value of f of x1, y1? You should substitute x1, y1 here. 1 plus value of y1. 1 plus value of y1, 2.75 over 1.25. Right. 1.25. Of course, it's hard to compute in mind. This will, I don't know what is this. You can use your calculators to compute. What? 3.55. Yes, maybe I don't know. I don't know. Well, and after that, using this 3.55, we can compute y3. You can compute y3 when you substitute y2 and x2 into the formula. Well, is it clear how to compute the values of y step by step? We know the value of f0 and x0 and f0. Using this value, we can compute the value of x1 and y1. If you know x1, y1, you can compute x1 by x2, y2, and so on. And after that, you can build a table of the values. Okay, but pay your attention that these values are not the real values of the function, the solution. It's some approximation. In the exercise B, the real solution is written here. Please look to the exercise 2 and under the letter B. It's written the real solution to the problem B. The real solution is y of x equals to x logarithm x plus 2x. Suppose that somebody tells us, as I tell you, that this is a real solution. Let's compare the values of approximate solution with the real one. How to do it? You should substitute x, because x we know exactly. Please compute y of x0. Please compute y of x0. Again, exercise 2 letter B is given the real solution for the problem in the exercise 1 letter B. Please compute the value of the function at the point 1, the real value. This is the real function. Y of xi. What is the value of x? What is the value of y of x1, x0? This is the formula, just substitute here 1. This is the formula, the real solution. X1, sorry, x0 equals to 1. 1 logarithm 1 plus 2. Logarithm 1. What is the value of logarithm 1?
It's 0.
0, right. Logarithm 1 is 0. So the value of the value of the function at the point 1 is 2.
2.
Exactly 2. Value at the initial point is the same. And this will be true for any initial valued problem. That the initial point must be the same. What about the next point? Please substitute 1.25 here and compute the value of y of 1.25. And tell me the answer. What is the value of y of 1.25? Of course, you should use your calculators to compute it, because the value of logarithm, except the point 1 cannot compute in mind. 2.77. Yes, maybe. I don't know. I know that this value, it must be similar to this. These two values should be close. 2.77 and some other values. Yes, yes, maybe. And the next point, 1.5. Please compute the last point, y of 1.5. Y of 1.5. What is the value of the function at the point 1.5?
309.
301.
9.
309.
Yeah.
Yes, maybe. I don't know. What? 306? 306. 2 students have 306. I don't know. 306. But you can use your calculator to check. But yes, it seems to be correct. Why? Because 360.
No, 06.
Господи.
$360, sir.
What?
360.
360.
360, yeah.
360.
Yeah.
Okay, maybe. I don't know. 360. Okay. Okay. Well, what I know that after we compute the actual values of y, we can compute the error. Error is a difference between real value and approximation. What is the error at initial point? What is the error at initial point? It's 0. Error at initial point is 0. 2 minus 2 is 0. What is the error at the first point? 0.02. What is the error at the second point? 0.05. And if you compute the next point, the error must be greater. So step by step, the error is increased. The error is increased. Okay. I think you understand how to apply Euler method to find approximated solution. You know the equation, you know the initial condition, you know the step. Step may be any step that you take, 0.25, 0.1, and so on. And after that, point by point, we can compute approximated solution. Well, let's show you the geometric interpretation of the Euler's method. Suppose that we have the function y prime equals to f of ty. Here it's used notation t for the variable. And this is a graph of the function y of t. We don't know y of t, but at the initial point, we know the derivative. And the derivative from the geometric interpretation of the derivative is the slope of the tangent line. And we can compute the approximated value of the function as a point at this line. At a moment t1, we can find the value on this line and compute the approximated value. After that, we can take this value and compute next approximation, next, and so on. So here, one step of the Euler method is shown in left figure, and a series of steps is shown on the right figure. Okay, and at the end of the lesson, let me show you how the Euler method can be implemented in Visual Studio. Let's take the problem that we consider as a first example. What is the problem from the first example? The f of xy is y. Please look to the Visual Studio. F of xy is y. It's the right-hand side of the equation. The exact solution in this case is 2 times e power x. How to apply Euler method? It's very simple. This is the main loop. This is the main loop. First, let me assign the step. Suppose that I want to carry out size of the steps in the interval from 0 to 1. And in this case, the step can be computed as 1 over size. x0, y0 are initial condition. To compute the table of the values, let me declare the variables xi, yi. The initial values of xi and yi are x0 and y0. And in this loop, I compute new value of x as current value plus h and new value of y as a current value plus h times f of xi yi. So as you see, I exactly follow this notation. yi plus 1 equals to yi plus h times f of xi yi. And new value of x is x1 plus xi plus h. Let's run this program, and in this loop there is an output statement where I output to the screen the value of x, the value of y, the value of exact solution, and an error, the difference between approximation and the exact value. Okay. Yeah. This is a table of the values x, y, the real value, and their error. Please look. The error becomes larger at any step by step. The error is increased. At the initial point, the error is 0. Next point, the error is 0.01. Next, 0.023, and so on. The error becomes larger. It will be useful to compute the maximum, the largest error. Let's declare the largest error as max. And let's find the sorry. Алексей, если не срочно, то я перезвоню через 20 минут. Let's find their maximum error. If current error greater than max, then max equals to current error. After the loop, let's output the largest error. Error equals to max. Well, here the largest error is 0.249. Well, let's consider the same problem, but let's decrease the step. Let's take the step 0.01. And we see that the largest error also decreased 0.027. Let's take the error, sorry, not error, the step the step 10 times smaller. And the error becomes 10 times smaller too. .003. So here, like in any other numerical method, if you apply this method for the large step, you get large error. If you decrease the step, the error will be decreased. The error becomes smaller when you take the step smaller. Well, in the presentation is also written some slides about more complex methods, second order Runge-Kutta methods, but we skip it. We consider only the first, only the Euler method. I think it will be enough. Well, I don't remember exactly when your lessons are finished. Maybe it will be next week or week after week. I don't remember the schedule, but in any case, the next week this room will be busy again, and next week, if we have a lesson, the lesson will be online, and at this last lesson, maybe before the lesson on Monday, I will send you the tasks that I ask you to solve. Some list of problems that we consider during our lessons. Of course, not all of the problems, but the typical problems. I will send you this task and I ask you to solve it and send me back your solution. You can solve it on paper and send me the photo or scan of your solution. More or less the same problems will be on the exam.
On the exam, are we going to implement that?
Oh, no, no implementation. Just apply some method. For example, related to our today topic, you have a differential equation. Apply compute 3 points using Euler method. Something like this. Compute the error of approximation. Well, next week, our lesson will be online, and I will send you the task that I ask you to solve and send me back your solution. Or maybe I ask you just to upload your solution on a Google Drive, but maybe just you use a mail. I ask you to solve it to send me the task by mail. That's all for today. Let's finish our lesson.